We're talking about section 2.4, interpretations of the derivative. And I want to start with just some notation because there are many different ways we can show the derivative. So one that we have done quite a bit and that's very popular is that f prime of x notation. That represents the derivative of f. But another one that you'll see a great deal is this dy dx notation. This is referred to as Leibniz notation because he was the one that came up with that. And what he was trying to suggest with his notation, and he was very thoughtful in his notation, is that it's the limit as delta x goes to 0 of that delta y over delta x. So again, thinking of slope as the change in y over change in x, and then you're letting that h, that denominator, that delta x go to 0. And so as that goes to 0, then those deltas change to the d's in the notation. You will also see it written like if you want to show sometimes the operation of taking a derivative, it'll be written as taking the derivative of f of x. So that d dx notation means we're going to take the derivative of whatever follows. And sometimes you might see it, for example, like take the derivative of, and then we might have a function like x to the third minus natural log x, and that means that you're going to apply the derivative or differentiate whatever follows there. Sometimes we'll see it written as df dx, so that Leibniz notation, but instead of y, it might be the f standing for function, or we'll see a lot of times derivative of whatever the name of our function is with respect to whatever that independent variable is. So ds dt is one we see a lot because particle motion, for whatever reason, is often referred to as s of t. So it's saying take the derivative of that s function, and that's the independent variable that we're taking the derivative with respect to. Now, to evaluate a derivative, there are a few other notations as well. So, for example, if we want to evaluate the derivative at 3 using our f prime notation, that works really nice. F prime of 3 makes sense with what we've done with functional notation in the past. You're going to find the derivative function and evaluate it at x equals 3. Not so nice is the Leibniz notation. So when you do that, you'll see the dy dx, then you'll see this straight line written there, just that kind of bar, and then at the bottom they'll say evaluate it at x equals 3. So not nearly as user-friendly as the prime notation there. So units are going to be very important. We're going to talk about those in a moment. Let me just insert into here because this will come up somewhere in the future, and so I can at least make mention of it now, and we'll revisit it later. But we will find oftentimes equations of tangent lines, which we understand what that means. Hopefully, if there's some kind of curve and we have a particular point, then we're talking about that line that just kind of grazes that curve at that point. That's what we mean by a tangent line. Now, there's also what is known as a normal line. So a normal line is perpendicular to the tangent line at the point of tangency. So, for example, in the picture that we have there, where we have that tangent line in yellow, a normal line would be perpendicular to that, and it would still contain that point of tangency, that point on the curve where the tangent line intersected it. Okay, so we also want to understand that the units. The units are matter. So when we're talking about a derivative, it's always going to be a rate of change, but it is a rate of change. And so that means that the average rate of change, which we have talked about a great deal in AP Prep, the average rate of change has the same units as the instantaneous rate of change, has the same units as the derivative. So a derivative, and I think you see it nicely again in that Leibniz notation, that it's that rate of change of y with respect to x. So just like we saw with finding slopes or average rates of change, we're going to have those same units that we will now introduce with our derivative. So we're going to look at a few examples. So suppose the cost of building a house, with area, say capital A, is given by capital A square feet. So let me put the units in there. So capital A square feet is given by some unknown cost function C of A. So we're assuming now the cost is going to be in dollars, and that's for an area, for a house that has an area of capital A square feet. So then the question becomes, thinking about units now, what does, say, C prime of A, which could also be written as, in Leibniz notation, dc dA, represent? And when I say that, I mean, what would the units be? So in particular, you can think about that for a moment. Suppose I give you some actual numbers. So suppose we say C prime of 2500, which can also be written as dc dA, evaluated at A equals 2500. And suppose we say that is equal to, we'll say 125. So what does that mean in the context of that problem? And can we use the correct units? So again, it's a rate of change. So it's and since that's a positive, that means it's going to be increasing. So the cost of, say, building a house that we've already made, that is 2,500 square feet. So that's what that 2,500 means. So we've already built the 2,500. So this is going to be the cost of building a house 2,500 square feet is going to be $125 per square foot. So the cost of building the house is going to be different at different times. You know, if you're digging the hole, you're starting to frame it out, you're actually, doing more. So what we're saying is, so it changes with different square footage. So what this is saying is that if you've already budgeted for a 2,500 square foot, the cost of building one more square foot onto that 2,500 square foot house will be $125. So it's $125 per square foot. This is sometimes referred to as the marginal cost. So a lot of economists and stuff will use the term marginal cost there. So let's do a slightly different example. So let's say the cost of extracting coal. So the cost of extracting coal from the ground is given by C equals F of T, and we'll say the cost is in dollars, and the T is tons of coal. So that function is going to tell us the cost of, now let me make this be a capital T because that's tons of coal, not time. And so then the question is, what does F prime of, say, 750 equals 60 mean? So then we want to use the correct units, and we want to give it that context. So again, a derivative is a rate of change, and that's positive. So it would be then the cost of extracting more coal after we have already removed 750 tons is going to be, and here's our units, $60 per ton. Okay, and that again would be thought of as a marginal cost in the context of this problem. Okay, here's a different one. Let's say water is leaking from a storage tank at, we'll say, 5 cubic feet per minute. 5 cubic feet per minute. Can we interpret this rate as the derivative of a function? So this is kind of going in the reverse order here. So in the other one, we gave you the function and we told you what the function meant. We said, now then tell us what the derivative means. Here now we're getting a rate of change. So we can see this feet cubed per minute is a rate. So in the what would the context then be? What would our function be here? So that 5 is the derivative of, and our clue is going to be the units here. So it's going to be a rate of change of something measured in volume. So Leibniz notation is kind of nice. It's a dV, a change in volume, over a change in time. And so we could either write it as dV dt, or we could say, even say V prime of t is going to be, and if it's leaking, that means that volume is decreasing, so we would say it's going to be a -5. So it's a rate of change of a volume. Okay, I'm going to get a new panel. We're going to talk about some tough ones here. I'm going to pause it for a minute so I can write it down, and you don't have to wait for me to write it. So as we look at these questions, let's start with number 1, G of 4 equals 129. So you can see in the green that the G is representing how many electric cars there are in the US measured in thousands, and that the T value is the number of years since 1995. So this 129,000, this is representing 129,000 electric cars 4 years after 1995. So maybe a little more clearly stated, we would say in 1999, there are 129,000 electric cars in the US. Now moving to the second one. Now this is the derivative means it's a rate of change. So it's going to be a rate of change of the G with respect to T. So that's going to help think of the units there. So that's going to be a change in thousands of electric cars per year. So this is saying that in that 1999, the number of electric cars in the US is increasing, since that's positive, by 29,000 per year. Okay, moving over to number 3, the inverse. These are always tough. So we're switching now the independent and dependent variables. So now the input value is not going to be years, it's going to be thousands of electric cars, and the output value is going to be our years. So trying to say this in a way that kind of makes sense can be challenging, but something like the number of electric cars in the US will reach 640,000 10 years after 1995, so in 2005. So another way of saying it is going to take until 2005 for the number of electric cars in the US to reach 640,000. Now, even more challenging is we look at this derivative. So it's going to be a rate of change of now, it's not dg dt, but it's going to be switched. So it's going to be a dt over dg. It's going to be a change in time per G measurement. So change in time per 1,000 electric cars. Kind of a weird idea. But what that's saying is that once there are 640,000 electric cars in the US, then it will take 0.0128 years per increase in 1,000 electric cars. So you might think of that as being, it's going to take 0.0128 years for the US to get the next 1,000 electric cars once it's reached 640,000. And I think that's pretty small, like somewhere in the neighborhood of 4 or 5 days. Okay, see what you can do with homework 19.